Welcome to today's lecture on lightweight design. So far we learned about why it is important to save weight and why it is also important to take the costs into account. Today I want to discuss some basic rules on structural optimization, that means on lightweight design. That means we want to go more into detail, more into the deep of the concept of lightweight design. And I want to start with the first statement of our basic design rules, and this statement is that you have to exploit the full load carrying capacity of your structure. Well, this is a very easy and, of course, naturally clear statement. Where's the challenge? Well, the challenge is that when you want to exploit the full load carrying capacity of your structure, you have to know everything about the loads, for example. And this is very hard. You have to know the real loads which your structure, which acts on your structure during service, for example, in advance during the design phase. Or you have to do an exact sizing. It means you need exact sizing methods. You need the exact definition of your design service goal, for example. And all these prerequisites you need makes it so sophisticated and complex to exploit the full load carrying capacity of your structure. The second rule you have to have in mind is that you should prefer tension-loaded parts. Why? Well, when you have a tension-loaded part, I will demonstrate in this sheet of paper. It's very simple to calculate. Here now I apply my tension force. When you apply compression, you have to deal with an additional phenomenon. And this phenomenon is called the phenomenon of stability. Here, for example, you see when I apply tension, okay, my plane sheet stays plain, but when I apply compression, I have a large deformation of my structure. That means compressive forces reduce the load carrying capacity of my structure significantly. And this is the reason why I should prefer tension-loaded parts. The next rule is that I should introduce loads directly. Why? Well, again, we take this sheet of paper and we redirect our tension force by this fold. That means the force is not on the direct way between my two hands, but we redirect it via the fold. And then you see that I have additional bending of my sheet of paper. That means that redirection of loads means that we have additional section forces in our structure. And this additional section forces in our structure, although we have the same external loads, these additional forces, they reduce the load carrying capacity of my structure too. So therefore, introduce your loads directly. And when you introduce loads in lightweight structures, that means optimized structures, you have to take a special focus on the load introduction points, because these points are always very critical. You have very thin structures, for example, again, sheet of paper, very thin structure, and the point where you apply your load, this always undergoes very large deformations and therefore fails at a very early level of loading, and therefore you have to take a special focus during design on these load introduction points. The next rule you have to have in mind is that you should use the inner force balance. I will explain you in the next lectures the mechanical background. Here just one simple demonstration. What does it mean, the inner force balance? Take this simple paper roll, and on this simple paper roll I apply a torque. And there you see that nothing's happened to your paper roll. So this is a very, very optimal structure for a torque loading. And now I have the structure. It's the same cross section, the same thickness, that means the same weight, and the only thing I do is I cut it right in the middle. So the same weight, the same geometry, just this cut. And now I apply again this torque, and then you will see that now my structure becomes very, very flexible. The load carrying capacity decreases significantly just by applying this cut. And by applying this cut, I prevented the structure to use this inner force balance, and this is a responsible factor for this very, very bad structural behavior. So the rule is you have to use the inner force balance. Prefer integrated design is also important. When you have differential design, that means you have several parts, you have to join these parts. And each joining means that you have an overlapping length. And in this overlapping length, you have twice the thickness. And this increases, of course, your weight. And when your joint is not an adhesive joint, but a riveted joint, you have also, in addition, the weight of the rivets. So each joint means additional weight to your structure. So please try to make an integrated design where you have no joints. Also, design large moments of inertia. What does it mean? Well, I can again show you on this simple example of a sheet of paper. Well, take this sheet of paper, plain sheet of paper, and this should carry its own weight, and you will see that it fails. We have a very, very large deformation, and when you think, well, this should be a ceiling, a floor ceiling or something like that, you will see, well, you can't use this, so the structure fails, even carrying its own weight. And this is because the second moment of inertia is rather small, because the thickness is rather small. But when I rotate the paper just by 90 degrees, now the width becomes so high, so I increase the second moment of inertia significantly, and now the sheet of paper is able to carry its own weight. So use the second moment of inertia and design your structures in a way that you maximize the second moment of inertia. And when you are in the situation that you have to use this plane and bad orientation of your structure, then please apply some curvature to your structure. Because when you apply some curvature to your structure, here you see, then you use the so-called spatial effect, and this increases the load carrying capacity of your structure significantly compared to pure plane structures. Just by applying a rather shallow curvature, I will see that the sheet of paper is able to carry its own weight. And last rule is, okay, we saw that we have problems when we have a compressive load on our paper. So please apply some stiffeners. And these stiffeners I can realize, for example, here in this case by a simple fold. So I will fold my sheet of paper, and this fold acts as a stiffener. Here you see, now I have a stiffener, and these stiffeners have to be applied in principle loading direction. Here in this case I apply my compressive force in that direction, so the stiffener has also to be in that direction, because when it's perpendicular to it, it has no effect on buckling or on increasing the buckling stiffness. So these were the basic design rules. When you have these rules in mind when you do a design of your structure, I can guarantee that you get a proper design of your structure. But the mechanical background on these rules and why these rules work, this is something I will show you in the later on lectures. Thank you so much for your attention.